Hello, and thank you very much for giving me the opportunity to present our work at the IEEE Sensors Conference 2020. My name is Martin Angerer, and I'm a PhD student at the Karlsruhe Institute of Technology working on ultrasound transducers. In the next few minutes, I want to present you a semi-automated packaging of transducer arrays for 3D ultrasound computer tomography. So what is 3D ultrasound computer tomography? It's a tomographic imaging approach based on ultrasound. Here you see our second generation prototype device for breast cancer screening. The patient lies prone on top of the device while one breast at a time is immersed into this water-filled measurement container and scanned. This container holds 157 transducer arrays with 16 transducers integrated in each array. So how does it work? Each individual transducer emits at a time an unfocused ultrasound wave while all other record. Depending on the time of flight of the acoustic wave, we can differentiate between transmission and reflection signal. And this can be mapped to different physiological modalities such as speed of sound and reflectivity of the tissue. Using this setup, a first clinical pilot study was conducted in 2012. Here you see some of the results on the left-hand side for comparison, a MRI image using contrast enhancements where a large lesion was detected here in this region. On the right-hand side of approximately the same position, one reconstructed USCT image. The cancerous tissue was thereby detected by thresholding the speed of sound. So this study was in general a success and we learned a lot, and based on this we optimized the design. Based on these optimizations, several transducer array requirements were derived. From the functional point of view, we want to increase the bandwidth and the opening angle to improve the overall image quality and increase illumination of larger breasts. To reduce artifacts, we also want to randomly distribute the transducers. From medical device regulations, we have to be safe, non-toxic and reliable. And from production, we want to reduce the costs and speed up the production. So especially the last two requirements led to the semi-automated packaging approach. First now, a few words to the main innovation of the new transducer array. These are Piezocomposite discs. So for that, 18 single PZT fibers with a diameter of 460 microns are integrated in a polymer disc. The position indicated here was previously simulated and found to be optimal to simulate pseudo-random distribution. On top and bottom side of the transducers, electrodes are printed. In addition to the transducers, several supporting structures like holes for pins and for placing a miniaturized temperature sensor are foreseen. Also, the printing includes several fiducial marks for automatic detection. So how to integrate this PZT disk then in a fully functional array? So we decided for a stacked process assembly. For that, the first layer, a PCB disk was chosen. This printed circuit board connects the transducers with the front-end electronics. One detail I want to mention here are the concentric grooves which are milled around the pads to avoid short circuits caused by displaced conductive adhesive. Also the drill holes here, which are mainly directly behind the transducers, which allow a direct application of backing material onto the backside of the transducers. In front of the PCT disk, a matching layer disk is placed. For that, we chose a thermoset microwave material as it exhibits an intermediate acoustic impedance in between the piezo and the water. The material comes with a 35 micron thick copper layer on top. This copper layer is structured using a wet etching process to form additional fiducial marks and spaces for a uniform bonding layer between PZT disk and matching layer. So now to the assembly, we start with the PCB, where On top of the pads, using a stencil printing process, conductive adhesive is applied. The next step, the PCT disc is picked and placed using an automatic die bonder onto this PCB. Then a screen printing process using again conductive adhesive is applied on top of the PCT disc to connect the ground electrode with the PCB. Then on top of that, an additional layer of mechanically more durable adhesive is applied to connect the matching layer. Then the backing material is applied in the designated holes using a polyurethane tungsten compound. This is beneficial in two ways. So the polyurethane exhibits high attenuation for backside emitted acoustic waves, and the tungsten increases the acoustic impedance for higher damping and therefore higher bandwidth. In the last step, this stack is then integrated into a plastic housing using biocompatible glue. So here, just a short video I want to show you of one of the pick and place processes. In this one, the matching layer is placed on top of the pre-processed stacks. The matching layer comes from the flip chip carrier, is then here inspected, then automatically positioned here. The drop-down velocity is chosen relatively slow, and high drop-down force of 20 Newton was chosen to ensure high bonding layer uniformity. So to ensure full functionality of the arrays, we conducted electromechanical impedance measurements before and after the assembly. Here you see the results before the assembly for 144 transducers, which corresponds to 8 arrays. Few words to the functionality. For frequencies below 1 megahertz, the transducer almost purely behave capacitive. Here in the center, you see the thickness resonance, and for higher frequencies, the planar resonance mode, which is less prominent. In comparison, on the right-hand side, the same transducers measured after the assembly. Here you see a significant drop in overall low frequency impedance, as well as high attenuation of the thickness resonance. To assess this quantitatively, we extracted 4 properties from the electromechanical impedance measurements. These are at first the low frequency impedance, then the series and parallel resonance frequencies, which allows us to calculate the effective electromechanical thickness mode coupling, as well as the phase angle at resonance. This slide now shows you the differences between these 4 properties before and after the assembly. Starting with changes in the series resonance frequency, there a slight shift towards 2.3 megahertz was detectable. This shift towards higher frequencies is caused by additional stiffening of the resonator due to adding the matching layer. This change in stiffness is reflected here in a reduction of the effective coupling too. This is an undesired effect, but a trade-off for obtaining good coupling between the piezo material and the front water. The effect of the backing material is mainly reflected here for the phase angle at thickness resonance, where a drop of more than 80 degrees was measurable. For the impedance magnitude at lower frequencies, we measured a drop of 20 kilo ohm in average, which is mainly caused by increased line capacitance due to the PCB. This is beneficial in one part as it reduces the necessity for impedance matching of the front-end electronics, but may cause additional crosstalk. So as you can see here, most of these properties show that 4 transducers deviate significantly from the mean values before and after the assembly. These are actually the same transducers. This means that none of the measured transducers showed non-functionality after the assembly. Also, especially these 2 parameters seem suitable for one-dimensional quality control assessments. For example, by placing placing a threshold here, we can differentiate between fully functional transducers before and after the assembly, and here even for incoming inspection to differentiate between good and bad for incoming inspection. Based on these results, we think that with the presented manufacturing, we can produce reliable transducer arrays for our new 3D USCT generation. The throughput is scalable due to the batch production, so especially by interleaving the batches, this can be highly scaled. In addition, the layer-by-layer stacking allows optimization of single components without changing the overall process. Of course, there's always room for improvement, so we still rely on several manual processes. Especially the use of low temperature curing adhesive is very time consuming at the moment. So this sums up to approximately 1 week for each batch production. Also, we encountered several problems with the positively printed fiducials here. So by using negatively printed fiducials, thereby the detection quality of the automatic die bonder, pick and placer die bonder could be enhanced. Also, to get rid of the conductive adhesive application here for ground connection would be beneficial. So by integrating also already a conductive material directly in the disc would make this process step negligible. So then finally to the next steps. These manufactured transducer arrays were then tested in an ultrasound environment and then integrated into our measurement container here, which allows us finally test imaging. Then to assess the long-term functionality of the transducers, we want to conduct accelerated aging tests by applying elevated temperatures and voltages to the transducer arrays. With that, I want to conclude my talk and thank you very much for your attention.